Okay, so good day, everyone. Our topic for today is about memory management in our operating systems applications. So this will be the learning objectives or course intended learning outcomes for this lesson. So in a unit programming system, main memory is divided into two parts. One part for the operating system, then resident monitor or kernel, and one part for the program currently being executed. In a multi-programming system, the user part of the memory must be further subdivided to accommodate multiple processes. The task of subdivision is carried out dynamically by the operating systems and is known as a memory management. Effective memory management is vital in a multi-programming systems. If only a few processes are in memory, then for much of the time, all of the processes will be waiting for input-output. In the processor will be idle. Thus, memory needs to be allocated to ensure a reasonable supply of ready processes to consume available processor time. So, we begin with the requirements that memory management is intended to satisfy. We need to define a variety of simple schemes that have been used for memory management. So, this figure introduces some key terms of our discussion. A set of animations and illustrated concept in the chapter is available also. So we have frame, page, and segment. While surveying the various mechanisms and policies associated with memory management, it is helpful to keep in mind the requirements that memory management is intended to satisfy. And these requirements include the following: relocation, protection, sharing, logical organization, and the physical organizations. Relocation in a multi-programming systems, the available main memory is generally shared among a number of processes. Typically, it is not possible for the programmer to know in advance which other programs will be resident in the main memory at the time of execution of his or her program. In addition, we would like to be able to swap active processes in and out of main memory to maximize processor utilization by providing a large pool of ready processes to execute. And once a program is swapped out of disk, it would be quite limiting to specify that when it is next swapped back in, it must be placed in the same main memory region as before. Instead, we may need to relocate the process to a different area of memory. Thus, we cannot know ahead of time where a program will be placed, and we must allow for the possibility that the program may be moved about in the main memory due to swapping. And these facts raise some technical concern related to addressing as what we have here in our 7.1, addressing requirements for a process. The figure depicts a process image. For simplicity, let us assume that the process image occupies a contiguous region of main memory. Clearly, the operating system will need to know the location of process control information and of the execution stop, as well as the entry point to begin execution of the program for this process. Because the operating system is managing memory and is responsible for bridging this process into main memory. These addresses are easy to come by. In addition, however, the processor must deal with the memory references within the program. Branch instruction contains an address to reference the instruction to be executed next. Data reference instruction contains the address of the byte or word of the data reference. Somehow, the processor, hardware, and operating system software must be able to translate the memory references found in the code of the program into actual physical memory addresses, reflecting the current location of the program in the main memory. Then the next one will be the protection. Each process should be protected against unwanted interference by other processes, whether accidental or intentional. Thus, program in other processes should not be able to reference memory locations in a process for reading or writing purposes without permission. In one sense, satisfaction of the relocation requirement increases the difficulty of satisfying the protection requirement because the location of the program in main memory is unpredictable. It is impossible to check absolute addresses at compile time to assure protection. Furthermore, most programming languages allow the dynamic calculation of addresses at runtime. Say for example, by computing an array subscript of pointer into a data structure. Hence, all memory reference generated by a process must be checked at runtime to ensure that they are refer only to the memory space allocated to that process. Fortunately, we shall see that mechanism that support relocation also support the protection requirement. Normally, a user process cannot access any point of the operating systems, neither program nor data. Again, usually a program in one process cannot branch to an instruction in another process. Without a special arrangement, a program in one process cannot access the data area of another process. The processor must be able to abort such instruction at the point of executions. We need to take note that the memory protection requirement must be satisfied by the processor or the hardware rather than the operating system or software. This is because the OS cannot anticipate all of the memory references that a program will make. Even if such anticipation were possible, it would be prohibitively time-consuming to screen possible to assess the permissibility of a memory reference, the data access or the branch. At the time of execution of the instruction making the reference, to accomplish this, the processor hardware must have that capability. Next will be the sharing. Any protection mechanism must have the flexibility to allow several processes to access the same portion of a main memory. Let's say, for example, if a number of processes are executing the same program, it is advantageous to allow each process to access the same copy of the program rather than have its own separate copy. Processes that are cooperating on some tasks may need to share access to the same data structure. The memory management system must therefore allow controlled access to shared areas of memory without compromising essential protection. Again, we will see that the mechanism used to support relocation support sharing capabilities. Next will be the logical organizations. So, almost invariably, main memory in a computer system is organized as a linear or one-dimensional address space consisting of a sequence of bytes or words. Secondary memory at each physical level is similarly organized, while these organizations closely mirrors at actual machine hardware. It does not correspond to the way in which programs are typically constructed. Most programs are organized into modules, and some of which are unmodifiable, read-only, execute-only, and some of which contain data that may be modified. If the operating systems and computer hardware can effectively deal with user programs in data in the form of modules of some sort, then a number of advantages can be realized, as is stated here in our presentation. So it means to say that then the physical organizations. Computer memory is organized into at least two levels, referred to as a main memory and secondary memory. Main memory provides fast access at relatively high costs. In addition, main memory is volatile. That is, it does not provide permanent storage. Secondary memory is lower and cheaper than the main memory and is usually not volatile. Thus, secondary memory of a large capacity can be provided for long-term storage of programs and data, while a smaller main memory holds programs and data currently in use. In this two-level scheme, the organization of the flow of the information between main and secondary memory is a major system concern. The responsibility for this flow could be assigned to the individual programmer, but it is impractical and desirable for two reasons. And this will be listed in our screen. It is clear then that the task of moving information between the two levels of memory should be a system responsibility. And this task is the essence of the memory management. Memory partitioning. The principal operation of memory management is to bring process into main memory for execution by the processor. In almost all modern multi-programming systems, this involves a sophisticated scheme known as a virtual memory. Virtual memory is, in turn, based on the use of one or both of two basic techniques, segmentation and paging. Before we can look at these virtual memory techniques, we must prepare the ground by looking at the simpler techniques that do not involve virtual memory. One of these techniques is partitioning. It has been used in several variations in some now obsolete operating systems. The other two techniques, simply paging and simple segmentation, are not used by themselves. However, it will clarify the discussion of virtual memory if we look first at these two techniques in the absence of virtual memory considerations. Fixed partitioning. In most schemes for memory management, we can assume that the OS occupies some fixed portion of main memory and that the rest of main memory is available for use by multiple processes. The simplest scheme for managing this available memory is to partition it into regions with fixed boundaries. So this figure shows example of two alternatives for fixed partitioning. One possibility is to make use of equal size partitions. In this case, any process whose size is less than or equal to the partition size can be loaded into any available partition. If all partitions are full and no process is in the ready or running states, the operating system can swap a process out of any of the partitions and load into another process so that there is some work for the processor. There are two difficulties with the use of equal size fixed partitions. Number one, a program may be too big to fit into a partition. In this case, the programmer must design the program with the use of overlays so that only a portion of the program need to be in main memory at any one time. When a module is needed that is not present, the user program must load that module into the program's partitions, overlaying whatever programs or data are hit there. Main memory utilization is extremely inefficient. Any program, no matter how small, occupies an entire partition. In this example, there may be a program whose length is less than 2 megabytes, yet it occupies 8 megabyte partition whenever it is swapped in. The phenomenon in which there is wasted space internal to a partition due to the fact that the block of the data loaded is smaller than the partition, it is referred to an internal fragmentation. Both of these problems can be lessened, though not solved, by using an equalized partition. In this example, programs as large as 16 megabytes can be accommodated without overlays. Partition smaller than 8 megabytes allow smaller programs to be accommodated with less than internal fragmentation. Okay, so placement algorithm. With equal size partition, the placement of processes in memory is trivial. As long as there is any available partition, a process can be loaded into that partition because all partitions are of equal size, it does not matter which partition is used. If all partitions are occupied with processes that are not ready to run, then one of these processes must be swapped out to make room for a new process, which one to swap out in a scheduling decision. This topic is explored later. So with an equal size partition, there are two possible ways to assign processes to partitions. The simplest way is to assign each process to the smallest partition within which it will fit. In this case, a scheduling queue is needed for each partition to hold swap out processes destined for that partitions. As what we have here in our A process queue per partitions. The advantage of this approach is that processes are always assigned in such a way as to minimize wasted memory within a partitions or the internal fragmentations. Although this technique seems optimum from the point of view of an individual partition, it is not optimum from the point of view of the system as a whole. So when it is the time to load a process into main memory, the smallest available partition that will hold the process is selected. If all partitions are occupied, then a swapping decision must be made. Preference might be given to swapping out of the smallest partition that will hold the incoming process. It is also possible to consider other factors such as priority and a preference for swapping out block processes versus ready processes. The use an equal size partition provides a degree of flexibility to fixed partitioning. In addition, it can be said that fixed partitioning schemes are relatively simple and require minimal OS software and processing overhead. The use of fixed partitioning is almost unknown today. One example of a successful operating system that did use this technique was an early IBM mainframe operating systems. Dynamic partitioning. To overcome some of the difficulties with fixed partitioning, an approach known as dynamic partitioning was developed. Again, this approach has been supplanted by more sophisticated memory management techniques. An important operating system that used this technique was IBM mainframes operating systems. An example, using 64 megabytes of main memory is empty except for the OS. The first three processes are loaded in, starting where the operating system ends and occupying just enough space for each space. As this example shows, this method starts out well, but eventually it leads into the situation in which there are a lot of small holes in memory. As time goes on, memory becomes more and more fragmented and memory utilization declines. This phenomenon is referred to as external fragmentation, indicating that the memory that is external to all partitions becomes increasingly fragmented, and this is in contrast to the internal fragmentation referred to earlier. One technique for overcoming external fragmentation is compaction. From time to time, the OS shifts the processes so that they are contiguous and so that all of time to time. The OS shifts the processes again, and they are contiguous and so that all of the frame memory is together in the block. So as an example here, compaction will result in a block of frame memory of length 16 M. This may well be sufficient to load in the additional processes. The difficulty with compaction is that it is time-consuming procedure and wasteful processor time. Note that compaction implies the need for dynamic relocations capability. That is, it must be possible to move a program from one region to another in main memory without invalidating the memory references in the program. Okay, so placement algorithm. Because memory compaction is time-consuming, the OS designer must be clever in deciding how to assign process to memory. So how to plug the holes. When it is time to load or swap a process into main memory, and if there is more than one free block of memory of sufficient size, then the operating system must decide which free block to allocate. Three placement algorithms that might be considered are best fit, first fit, and next fit. All of course, are limited to choosing among free blocks of main memory that are equal to or larger than the process to be brought in. Best fit chooses the block that is closest in the size to the request. First fit begins to scan memory from the beginning and chooses the first available block that is large enough. Next fit begins to scan memory from the location of the last placement and chooses the next available block that is large enough. In this figure A, the before, it shows an example memory configurations after a number of placement and swapping out operation. The last block that has used has a 22 megabyte block from which a 14 megabyte partition was created. In this one, after, it shows that the difference between the best first and next fit placement algorithm is satisfying a 16 megabyte allocation request. Best fit will search the entire list of available blocks and make use of the 18 megabyte block, leaving a 2 megabyte fragment. First fit result in a 6 megabyte fragment, and next fit results in the 20 megabyte fragment. Which of these approaches is best will depend on the exact sequence of process swappings that occurs in the size of those processes. However, some general comments that can be made, and the first fit algorithm is not only the simplest, but also usually the best and fastest as well. The next fit algorithm tends to produce a slightly worse result than the first fit. The next fit algorithm will more frequently lead to an allocation from a free block at the end memory. The result is that the largest block of free memory, which usually appears at the end of the memory space, is quickly broken up into small fragments. Thus, compaction may be required more frequently with next fit. On the other hand, the first fit algorithm may litter the front end with smaller free partitions that need to be searched over on each subsequent first fit pass. The best fit algorithm, despite its name, is usually the worst performer. Because this algorithm looks for the smallest block that will satisfy the requirement, it guarantees that the fragment left behind is as small as possible. Although each memory request always wastes the smallest amount of memory, the result is that main memory is quickly littered by block too small to satisfy memory allocation requests. Thus, quickly littered by blocks too small to satisfy memory allocation requests, thus memory compaction must be done more frequently than with the other algorithms. The replacement algorithm. In a multi-programming system, using dynamic partitioning, there will come a time when all of the processes in the main memory are in block state and there is insufficient memory, even after compaction for an additional process. To avoid wasting processor time waiting for an active process to become unblocked, the OS will swap one of the processes out of main memory to make room for a new process or for a process in a ready suspend state. Therefore, the operating system must choose which process to replace, because the topic of replacement algorithm will be covered in some detail with respect to various virtual memory schemes. We differ replacement algorithms until then. Body system. Both fixed and dynamic partition schemes have drawbacks. A fixed partitioning scheme limits the number of active processes and may use space inefficiently if there is a poor match between available partition sizes and process sizes. A dynamic partitioning scheme is more complex to maintain and includes the overhead of compactions. An interesting compromise is the body system. So presented with a request for an allocation of size k such that 2 raised to I minus 1 less than k or greater than or equal less than or equal to 2 sub I, the following recursive algorithm is used to find the whole of the size 2. So in this figure, it gives an example using a 1 megabyte initial block. The first request, A is 400 kilobytes, for which an 128K block is needed. The initial block is divided into two 512K bodies. The first of this is divided into two 256K bodies, and the first of this is divided into the 128K bodies, one of which is allocated to A. The next request B requires a 256K block. Such a block is already available and it is allocated. The process continues with the splitting and coalescing or occurring as needed. We need to take note that when E is released, two 128K bodies are coalesced into a 526K block, which is immediately coalesces with its body. This figure shows a binary tree representation of a body allocation immediately after the release B request. The left nodes represent the current partitioning of the memory. If two bodies are left nodes, then at least one must be allocated. Otherwise, they would be coalesced into a larger block. The body system is a reasonable compromise to overcome the disadvantages of both fixed and variable partitioning scheme. But in contemporary operating system, virtual memory based on paging and segmentation is superior. However, the body system has found application in parallel system as an efficient means of allocation and release for parallel programs. A modified form of the body system is used for Unix kernel memory allocations. The relocation. Before we consider ways of dealing with shortcoming of partitioning, we must clear up one loose end, which relates to the placement of processes in memory. With the fixed partition scheme, it is used that we can expect that the process will always be assigned to the same partition. That is, whichever partition is selected when a new process is loaded will always be used to swap that process back into memory after it has been swapped out. Thus, the location referenced by a process are not fixed. They will change each time a process is swapped in as shifted. To solve this problem, a distinction is made among several types of addresses. Number one is logical address. It is a reference to a memory location independent of the current assignment of data to memory. A translation must be made to a physical address before the memory address can be achieved. A relative address is a particular example of a logical address in which the address is expressed as a location relative to some known point, usually a value in the processor register. A physical address or absolute address is an actual location in the main memory. This figure shows the way in which this address translation is typically accomplished. When a process is assigned to the running state, a special processor registered, sometimes called the base register, is loaded with the starting address in main memory of the program. There is also a bounce registers that indicates the ending locations of the program, and these values must be set when the program is loaded in the memory or when the process image is swapped in. During the course of execution for the process, relative addresses are encountered, and these include the contents of the instruction register, instruction addresses that occurs in branch and call instructions, and data addresses that occur in load and store instruction. Each such relative address goes through two steps of manipulations by the processor. First, the value in the base register is added to the relative address to produce an absolute address. Second, the resulting address is compared to the value in the bounds register. If the address is within bounds, then the instruction execution may proceed. Otherwise, an interrupt is generated to the operating system, which must be respond to the error in the same fashion. The scheme of this figure shows it allows programs to be swapped in and out of memory during the course of execution. It also provides a measure of protection. Each process image is isolated by the contents of the base and bounds registers and safe from unwanted access by other processes. Now we may proceed to paging. Both unequal fixed size and variable size partitions are inefficient in the use of memory. The former results in internal fragmentation, the latter in external fragmentation. Suppose, however, that main memory is partitioned into equal fixed size chunks that are relatively small, in that each process is also divided into small fixed size chunks of the same size. Then the chunk of the process known as pages could be assigned to available chunk of memory known as frames or page frames. In this figure, it illustrates the use of pages and frames. At a given point in this, some of the frames in memory are used and some are free. A list of free frames is maintained by the OS. Process A is stored on disk, consists of 4 pages. When it is time to load the process, the OS finds for 3 frames and load the 4 page of process. Now, suppose as this an example that there are not sufficient unused contiguous frames to hold the process. Does this prevent the operating system from loading D? The answer is no, because we can once again use the concept of logical address. A simple base address register will no longer suffice. Rather, the operating system maintains a page table for each process. The page table shows the frame location of each page of the process. Within the program, each logical address consists of a page number and an offset within the page. In continuing our example, the 5 stages of process D are loaded into frames 4, 5, 6, 11, and 12. This figure shows the various page tables at this time. A page table contains one entry for each page of the process so that the table is easily indexed by the page number, starting at page 0, of course. Each page table entry contains the number of the frame in the main memory, if any, that holds the corresponding page. In addition, the OS maintains a single free frame list of all frames in main memory that are currently unoccupied and available for pages. So, thus we see that simple paging as described here is similar to fixed partitioning. The difference are that with paging, the partitions rather than a small program may occupy more than one partition, and this partition need to be contiguous. Now, the consequence of using a page size that is a power of 2 are twofold. First, the logical addressing scheme is transparent to the programmer, the assembler, and the linker. Each logical address, either page number offset of a program, is identical to its relative address. Second, it is the relatively easy matter to implement of functions in hardware to perform dynamic address translation at a runtime. So the following steps are needed for address translation. Number 1, extract the page number as the leftmost n bits of the logical address. Use the page number as an index into the process page table to find the frame number K. The starting physical address of the frame is K times 2 sub M. In the physical of the reference byte is that number plus the offset. And this physical address need to be calculated. It is easily constructed by appending the frame number to the offset. In our example here, we have the logical address, no? Which is page number 1, offset 478. And to summarize, with simple paging, main memory is divided into many small equal size frames. Each process is divided into frame size pages. Smaller processes require fewer pages, and larger processes require more. When a process is brought in, all of its pages are loaded into available frames, and a page table is set up. And this approach solved many of the problems inherent in partitioning. So in this example, this will be a 16-bit logical address with the available length based with process segment table and a 16-bit physical address for segmentations. Now, the segmentation. A user program can be subdivided using segmentation, in which the program and its associated data are divided into a number of segments. It is not required that all segments of all programs be of the same length, although there is a maximum segment length. As with paging, a logical address using segmentation consists of two parts, in this case, a segment number and an offset. Because of the use of unequal size segments, segmentation is similar to dynamic partitioning. In the absence of an overlay scheme or the use of virtual memory, it would be required that all of the program segments be loaded into memory for execution. The difference compared to dynamic partitioning is that with segmentation, a program may occupy more than one partition, and these partitions need not be contiguous. Segmentation eliminates internal fragmentation, but like dynamic partitioning, it suffers from external fragmentation. However, because a process is broken up into a number of smaller pieces, the internal fragmentation should be less. Whereas paging is invisible to the programmer, segmentation is usually visible and is provided as a convenience for organizing programs and data. Typically, the programmer or compiler will assign programs and data to different segments. For purposes of modular programming, the program or data may be further broken down into multiple segments. The principal inconvenience of this service is that the programmer must be aware of the maximum segment size limitations. So the following steps are needed for address translation, as stated here. So with simple segmentation, a process is divided into a number of segments that need to be of equal size. When a process is brought in, all of its segments are loaded into the available regions of memory, and segment table is set up. And this will be an example of a logical address, which is segment number 1, offset 752. The security issues. Main memory and virtual memory are system resources subject to security threats and for which security countermeasures need to be taken. The most obvious security requirement is the prevention of unauthorized access to the memory contents of processes. If a process has not declared a portion of its memory to be shareable, then no other process should have access to the contents of that portion of memory. If a process declares that a portion of memory may be shared by other designated processes, then the security service of the OS must ensure that only the designated process have access. The security threats and countermeasures discussed during our Chapter 3 lessons are relevant to this type of memory protections. So we have the buffer overflow attacks. A buffer overflow can occur as a result of programming error when a process attempts to store data beyond the limits of a fixed size buffer and consequently overrides adjacent memory location. This location could hold other programs' variables of parameters or program control flow data such as return addresses in pointers to previous stack frames. The buffer could be located on the slack, in the heap, or in the data sections of the process. The consequences of this error include corruptions of data used by the program, unexpected transfer of control in the program, possibly memory access violations, and very likely eventual program terminations. When done deliberately as part of the attack on the system, the transfer of control could be to code of the stackers choosing, resulting in the ability to execute arbitrary code with the privileges of the attack processes. Buffer overflow attacks are one of the most prevalent and dangerous type of security attacks. So, to illustrate the basic operation of a common type of buffer overflow known as stack flow, consider these three main functions, and this contains the three variables, the valid, str1, and str2, whose values will typically to be saved in adjacent memory locations. Their order in location depends on the type of variable, either local or global, and the language and compiler used in the target machine architecture. For this example, we assume that they are saved in consecutive memory locations from highest to lowest. And this is typically the case for local variables in C functions on common processors architecture such as in Intel Pentium family. The purpose of the code fragment is to call the function next_tag str1 to copy into str1 some expected tag value. So let's assume this will be the string start. It then reads the next line from the standard input for the program using the C library gets functions, and then compares the string read with the expected tag. If the next line did indeed contain the string start, this comparison would succeed, and the variable valid would be the string start to be set to true. The case is shown in the first of the three example program runs, and any other input tag would leave it with the value false, such as a code fragment may be used to parse some structured network protocol interaction for formatted text file. So, to exploit any type of buffer flow, such those we have illustrated here, the attacker needs to identify the buffer overflow vulnerability in some program that can trigger usually externally sourced data under the attacker control, and understand how the buffer will be stored in the process memory, and hence the potential for corrupting adjacent memory locations and potentially altering the flow of execution of the program. So to exploit any type of buffer overflow such as those we have illustrated here, the attacker needs to do this one. Defending against buffer overflows, compile time defenses, which aims to harden programs to resist attacks in new programs. Runtime defenses, which aim to detect and abort attacks in existing programs. So absolute loading. An absolute loader requires that a given load module always be loaded into the same location in main memory. Thus, in the load module presented to the loader, all address reference must be to specific or obsolete main memory addresses. For this example, the location of 1024, then the first word in the loaded module destined for the region of memory as address 1024. The assignment of specific address values of memory reference within a program can be done either by the programmer or the compile or assembly time. And there are several disadvantages for the former approach. This will be that address binding and the binding time and the linger time. So with all memory reference represented in relative format, it becomes a simple task for a loader to place the module in the desired location. So if the module is to be loaded beginning at the location X, then the loader must simply add X to each memory reference as it loads the module into memory. So to assist in this task, the load module must include information that tells the loader where the address references are and how they are to be interpreted. The set of information is prepared by the compiler or assembler and usually referred to as a relocation dictionary. Okay, so this will be the advantages. And that's what we have here, no? This will be the key terms of our discussion for today. This will be the possible review questions for you to be more competent and understand the topic. Now, one of the most important and complex tasks of an operating system is memory management. Memory management involves treating main memory as a resource to be allocated to and shared among a number of active processes. To use the processor and the I/O facilities efficiently, it is desirable to maintain as many processes in main memory as possible. In addition, it is desirable to free programmers from size restrictions in program development. The basic tools of memory management are paging and segmentation. With paging, each process is divided into relatively small, fixed-size pages. On the other hand, segmentation provides for the use of pieces of varying size. It's also possible to combine segmentation and paging in a single memory management scheme. So I think that's it for today, and thank you to our to the author of our books, no, as our references. Of course, the Operating System Internals and Design Principles, 7th edition by William Stellings. So that's it. Thank you and good day.